Hello, this is Mr. Manley, and today I'm going to give a lesson on function analysis. I want to talk about some things that you've probably seen before and some things that might seem a little bit new, and all of it is pretty intuitive except for the last part about odd and even functions, which may be new to you. I'm going to start off with, let's just talk a little bit about what a function is. And this is something that you should have seen before, the vertical line test. And the vertical line test is that if I get the graph of a function, as I have here, then if I've got the graph, then it is a function if it passes the vertical line test. That is there any way for me to draw a vertical line that hits the function in more than one spot? And the reason for that is a function is an input and an output, right? And the input is x. So x is the input, and then I have an output, y. And the function, the definition of a function says that we know what that output is going to be. And if it passes the vertical line test, then that is true. Now let's take a look at one that does not pass the vertical line test. Okay, so here's a graph, and that this is not a function does not mean that it's not significant or important. This is a shape that we recognize as a circle, and we could have an equation for that circle, but it wouldn't be a function. And if we look at the vertical line test here, I draw a vertical line, and here, if I enter this value of x, whatever value of x that is, say at like -3. So if I enter that value at -3, I could have this output or I could have this output. And there's the problem. With a function, when we have an input, we know what the output is going to be. So it's a special type of relationship, and the reason that we make the designation, or a reason to make the designation is that something is a function or something is not a function, has to do with calculus. And functions are a type of relationship that we can operate on using the calculus. And if it's not a function, then there are ways around that, but we always have to be talking in the language of functions in order to be using calculus. And so that's one of the reasons, at least, that we're interested in that distinction. Okay, so we've established that it's a function if we have it graphically by the vertical line test. We could also be asked, say, we could be given the equation, right? And I could say, oh, is y equal to x squared a function? And then I could say, is x equal to y squared a function? And the way that we're going to know algebraically whether or not it's a function, one, if we know what the picture is, and then we can do the vertical line test. And the other way that we would know is pretty much if you have an even power of y. So if we're looking at polynomials, at least. If you have an even power of y, it is not going to be a function. If you have an odd power of y, say I had, well, we have an odd power of y here, right? Y to the first. And if I had like y cubed equals x squared, that's going to be a function also. If I have, as I say, this odd power. See, an odd power of y, an odd power of y. Those will be functions. Even power of y will not. So that's just a little bit of a discussion about whether or not a relationship is a function if we're given the equation. And then the other thing that we could be given would be given a table of values, right? So we could be given this table here with x and y, and I could have 1, 2, 3, and I could have 2, 3, 4, and those inputs and those outputs indicate a function. But if I continued here and say I did 1 again, and I already did 1, and I have 3, now it's not a function because this 1 here an input of 1 gave me a 2, but then there was another input of 1 that gave me a 3. So back to that idea of a function, that when I have an input, I know what the output is going to be. There's no ambiguity there. All right, so let's talk about some of the, now that we talked about what a function is, let's talk about the function analysis. And some of this you've seen before, I'm sure. What is the domain of a function? So the domain of a function is all the allowable inputs of x. Now, if I look at this graphically, as I have down on the right here, I'm looking from side to side, right? And I'm imagining what values of x could I possibly see on the graph of this function. Now, in this case, I'd say I could get any possible value of x. So we're going to say that that is all real numbers. That would be one way to respond for the domain, all real numbers. And another way to respond is going to be with interval notation. And this is something that you may not be too familiar with, interval notation. And on the interval notation, for this one, I'm going to say from, that's the parentheses, to from negative infinity to infinity is how I would say all real numbers. The range for this one, looking up and down, if I look up and down here, is going to be from 2 and then down to negative infinity. Infinity always gets parentheses. The 2 here, this gets a bracket because the 2 here, if you look at the graph down on the right, at y equals 2, that's included in the function at y equals 2. So I get a bracket. If the 2 was not included, then I'd get parentheses. And then also just briefly talk about domain and range. If I were given the equation, say we're given y equals x squared, the domain of a function is always going to be all real numbers, unless there's a radical, in which case I have to say that I only want values of x that will make this positive. So in this case, the domain would be, if I use interval notation, I could have 0, and then I could go to infinity, but I couldn't have anything less than 0. And then if I went, and then another limitation on domain is going to be if there's a radical, not a radical, a fraction, so 1 over x, and then I could have everything except anything that would make the denominator 0. So the domain of a function, you just always want to say, oh, it's all real numbers, unless there's a radical or you have a fraction. One other that you're not familiar with, and it would take a lot of explanation for me to go into it now, would be if there's a logarithm, but we'll talk about that. You can talk about that when you get to logarithms. You can ask about the domain of a logarithmic function when you get to that. So these two you're familiar with, radicals and fractions. Okay. And then for these, just one last comment. For these, you just kind of have to think about, all right, well, what would the possible outputs be in order to get the range? What would the possible outputs be here? What are the possible outputs? And you just do that by a little mental analysis. Maybe you plug some points in, or if you know what the shape of the graph looks like, that can help you find the range as well. So there's no really direct step-by-step way to get the range here, but you want to think about things as we always think about things with functions. And let me just go back and say that. What we always think about with functions is we're always looking at being able to look at functions graphically and numerically and algebraically whenever we're doing our analysis. And we just use whatever way is going to help us answer the question that we want to answer, or we're going to look at the function in that way. Okay, increasing and decreasing. This is thinking about reading the graph from left to right. I am going to say that this one is increasing from negative infinity on the left and it's increasing until we get to 0. Now, do I put up to and including 0? I don't know, to be honest. I think it can depend on the context. So I can put up to and including 0. I could put up to but not including 0. We could look in the text and see what the text has to say about that. And I actually think if we look in the text that it's probably going to say parentheses, but that's not anything that we're going to really be sticklers about. For the decreasing for this one, it's going from 0, and then it's going to be decreasing infinitely. And understand that these, when you think increasing and decreasing, you think up and down, right? And you want to talk about where is it decreasing to or where is it increasing to, but that's not the way to think about it. The way to think about it is when is it, for what values of x is it increasing, and for what values of x is it decreasing. So it's not where it's decreasing to, but over what values is it decreasing, over what values of x. Okay? Let's see what else we've got here. Okay, we want to talk about maximum and minimum, and these are local or relative maximum and minimums. They're not absolute. So we're not talking about the absolute, the most maximum point or the most minimum point. That is not what we're talking about. We're talking relatively speaking. Relatively speaking, where is the maximum, where is the minimum? So relatively speaking, I've got a maximum here. Relatively speaking, I've got a minimum here. Relatively speaking, I've got a maximum here. Now, if I said where is the minimum, and I was saying the absolute minimum, I wouldn't be able to answer that, right? Because this, if you look down to the left here, this just keeps going down and down and down. So there is no minimum. It's decreasing infinitely. But we're talking relatively speaking. So now, relatively speaking, I can answer that question, and I can say that we've got a maximum at, looks like -4, 1, and I've got another maximum at, let's say, 1/2, and that looks like about 2, let's call it 2 2/3. So just estimating here, right? And then the minimum, I'm seeing I've got a minimum at approximately, I'll just call it -2, -2. And that's it for the relative maximum and minimum. Okay? And then finally, we talk about even and odd functions, and this is probably new to you. Even and odd, an odd function is symmetric with respect to the origin. Maybe I should have taken even first because that's easier. An even function is symmetric with respect to the y-axis. So that is, for every point on the left, I'm going to have the same exact point on the right. For every point on the left, I'm going to have the same point on the right. So do you understand that? Symmetry across the y-axis. And this makes the function even. For an odd function, now that was y-axis symmetry, right? Now, an odd function is not x-axis symmetry, because if I had x-axis symmetry, I wouldn't have a function. So think about that and make sure you understand that statement. If I had x-axis symmetry, I wouldn't have a function. So there is no x-axis symmetry. For an odd function, we're talking about origin symmetry. So that is for every point x, y. So let's say that I have this point here at -1, 1. I'm going to have that flipped. So I'm also going to have this point down here at 1, -1. If I have a point up here, I'm just going to let's just estimate and say, let's say that I had the point here at 2, 2, 3. I'm going to have the point down here at -2, -3. And I missed the, let's go back here, I missed the sign. I want to do the opposite. So it's going to be 1, I did get it right, 1, -1. I thought I didn't do the opposite of both of them. So the general statement would be for every x, y, I'm going to have -x, -y. Okay? So I'm gonna do another video on even and odd, but I'm gonna end this one here now.